Okay, so let's see here. There was a couple of things that I wanted to touch on before we move to gas. So we finished up developing this steady state, what we call rate equation for, in this case it was oil or a single phase liquid. We used oil, and hopefully the development of this was fairly clear from Darcy's law and the condition of steady state, which says that there's the same mass flux flowing everywhere. Okay? And then I'm going to make a few comments on this before we move forward. We talked about this equation being written. Of course, the units here, the 141.2 is partly, the 141.2 is including all these units conversions that we talked about, seconds and barrels to cubic meters and so forth. And I'll just to be complete, I'll just put the units for this equation, stock tank barrels per day. You've already had these, before. Millidarcies, thickness in feet. The concept of millidarcy feet is a concept that you will, at least if you're in reservoir engineering, you'll basically get used to. Pressures or PSI, because it's a difference, it doesn't really matter if it's PSI-A or PSI-G. I'll just put PSI. Viscosity was in centipoise, which is, fairly standard. Formation volume factor doesn't have a unit normally. It could, but it doesn't usually. It's volume per volume. And the radius of both E and RW should be the same unit, be it feet or inches. Probably it'd be feet because you don't measure the external boundary or the external distance in inches. So these need to be consistent. So this is pretty much the rate equation that's easy to develop, a simple kind of differential equation solution to that. So were there any questions about that before we move on? That's typically written as a productivity index, which is bringing all of the stuff outside, basically all of this stuff here, into a single constant, what we call the productivity index. Apparently this was commented on the Petroleum Scavel evening last week by one of the speakers, which this is a very important concept. Its units here would be stock tank barrels per day. Stock tank barrels per day per PSI. Okay? So and the magnitude of that can vary a lot because permeability and thickness and these things can vary orders of magnitude from one field to the next. So we're going to talk about that. So let's just look at the quantity and look at the range from well to well in the world. The quantity, the unit, and the range that you can expect. So we can start with permeability. This has got the largest variation from well to well. Permeability, we're using the unit of millidarcies. And the range traditionally would be, in Norway, it's probably the largest. The range, the maximum is around 10,000. I think Troll is around 10,000 millidarcies. I mean, 2,000 to, some of the rock is almost like sand that you see on the beaches. I mean, it's almost hardly consolidated. So this is the upper range, and this is often referred to in darcies because 1 darcy is 1,000 millidarcies. So this would be like 10 darcies, and anything greater than 1 darcy is extremely high. And so that's the upper range. Now, prior to the shale boom in the United States, the last 10 years, the lower range of permeability where we could produce economic amounts of oil and gas would be on the range of about, with a single vertical fracture, which was what we would have been using in the 70s and 70s and 80s to develop this, probably was on the low range for gas was 0.001, and for oil probably 0.01. Okay? So if you had a rock with 0.01 millidarcy, a light oil, maybe viscosity 0.5 centipoise, and you put a well through the formation and you fracked it, and maybe the thickness was 100 feet, you could make an economic oil rate for, you could pay for the well maybe twice, 3 times. So that's kind of the lower range pre-shale boom. Okay? Well, let's see how many orders of magnitude that is. That's 3, 4, that's 7 orders of magnitude. So let's just put orders of magnitude. Okay, 7. But that's before the shale boom. So the permeability that we have, like in the Bakken field, which is, well, it's actually probably on the range of 0.001. That's not really shale. But in gas, the shale gas, in particular in the United States that's being developed, is on the range of 10 nanodarcies. Okay, 10 nanodarcies is 10 times 10 to the minus 6 millidarcies. Okay? Well, but this is we're going from millidarcy to nanodarcy. So 10 to the minus 3 to 10 to the minus. So basically what we now have is 10. I'm going to write it this way, times 10 to the minus 6 is now the low range. That's 10 nanodarcy. And if you're going to get shipped off to the United States and one of these companies who are still surviving in the shale, that's the kind of permeability you operate with nanodarcies and not millidarcies. It's a whole different term. So 6 orders of magnitude different. So we're now down in the 10 nanodarcy range. We can actually make quite economic wells, gas and oil. Probably not so much oil in that range, but certainly gas. The really tight oil stuff in the United States that is making a lot of money, the Bakken field, the Permian Basin, and then parts of the Eagle Ford, where it's really containing oil, it's probably at minimum 100 to 500 nanodarcies, but it's still very low. So if we look at this, it's now 10 to the minus 5 to 10 to the 4th. So that's actually 9 orders of magnitude variation. And these are all, what I'm talking about, this is a well that's going to make us money. It's going to pay for the well and plus some. Any questions about that? Okay.
So one question, is the nanodarcy, is it like 10 nano millidarcies?
No. So a nanodarcy, well, let's just, so a millidarcy is 10 to the minus 3 darcies, and a nanodarcy is 10 to the minus 9 darcies. Okay? Which is the same as 10 to the minus 6 millidarcy. Okay? And in reality, as petroleum engineers, you have to have on your fingertips, okay? It's like millidarcy, darcy, and nanodarcy.
Is it a big or
Well, when you have only Darcy, the SPE uses capital D. Okay? But yeah, so it's capital D if it's only Darcy. If it's millidarcy or nanodarcy or even microdarcy, but nobody uses much microdarcy, it's little d. That's the SPE nomenclature. You can write it capital D. Many people do, but that's. I try to stick to the SPE standard. Okay? So that's at least 7 orders of magnitude and up to 9 orders of magnitude. Certainly for gas, it's 9 orders of magnitude. Okay? So, thickness, I'm going to move this down a little bit. Thickness, I'm putting in feet. Divide by 3 if you're a meters person. Okay? And we can start on the low end with 10 feet. Okay? For sure, you can have a 3-meter thick formation, and parts of the world you'll make money, so that's kind of a minimum, typically a minimum. And this can go to, like I told you about this field, the Cupiagua field in Colombia, the foothills of Colombia, is about 6,000 feet thick formation. Okay, it's so I'm gonna put 1,000, but it could be easily. It's not usual that it's more than 1,000 feet, but we could certainly have a couple of thousand feet. Okay, so there we've got 2 orders of magnitude. There. Okay. Pressure, the initial pressure, let's just say the initial reservoir pressure in PSI. If you want to think bar or atmospheres kind of thing, you're going to have to divide by about 15 to get it right. Divide by 10 if you're a driller. Well, no, they need pressures accurate too. So I mean, you have to divide, but this is going to range from probably the largest gas field in the United States, for example, is the Hugoton field. It goes Texas, Oklahoma, Kansas. It's about the same size, I think, as, I've forgotten I think it's around 30 TCF, 40 T. It's about like the Troll field. It's getting close to the size of the Troll field. But the initial pressure, I think, is like 400 PSI. And there are fields we've worked on in Iraq that are like 100 PSI, and they're like billions of barrels. Okay? So I'm going to put 100 PSI here as kind of a low end. Typically, you're up around 1,000 PSI, and you could certainly go to 15,000 and higher. But 15,000 is starting to get on the really high range. So I'm going to put 15,000 as kind of an upper limit. And probably 150 PSI is kind of a lower limit. But it can be less, and you can still have lots of oil there. So let's just say from 1,000 to 10,000, so that's from 100 to 10,000, so that's 2 orders of magnitude. Okay? And in principle, you can bring the bottom flowing pressure down to, close to the 100 PSI level, or close to 15 PSI. I mean, in theory, you could put a compressor on the top and bring it to even lower than 15 PSI. Okay? So that's the thickness, pressure, viscosity of oil. Yeah.
The edge thickness, is it the net thickness or the gross thickness?
That would be a net thickness. A hydrocarbon bearing, mobile. Yeah. But of course, the gross thickness could be often a factor of 50% more than that. It could be a factor of 10 more than that. But gross thicknesses would, but yeah, I mean, it's, yeah. Okay. If it's in the rate equation, it's net. It means that there's fluids flowing in that. We've got, for oil, we'll take the centipoise. That typically will be at a minimum 0.1 centipoise. That's a very light oil. You might have Smurbook South is an example of that, very light oil. You have to have a very high gas-oil ratio, so that's the low end. And if we go to the really high end where it's actually flowing, you probably can go to the at least 1,000 to the 10,000 range. Now, you may have to add some heat to get it to flow, okay? But I'm certainly going to put at least 100,000 centipoise here. And it can even be higher than 10,000, but then you have to put heat on it, typically, okay? So this is 10 to the 4th, 5 orders of magnitude, the oil viscosity. In the North Sea, we pretty much range from 0.2. In the Norwegian North Sea, I think 20 is about the highest you get. The Mariner field, which is on the UK side, is up in the hundreds. And that's a heavy oil in North Sea's connection with the North Sea. But if you go to Venezuela and Canada and probably some other places, you're getting into the hundreds, thousands, and 10,000 centipoise. I mean, it's gas viscosity is got a much lower range, 0.01 to 0.1. So that's 2 orders of magnitude. Right? 0.1 would be something like Kristen Field in the North Sea. It's at 900 bars. It's a rich gas. It's getting to a viscosity close to a light oil.
Isn't it just
Yep.
1?
0.01 to 0.1. Okay. You're always causing problems, sir. Just kidding. Okay. So it's not much. Okay. So do we have anything left? We got the RERW, BO. That's basically volume per volume, so it doesn't really have a unit. The BO can range from essentially 1 or close to 1 point. I'll put 105 because there'll be some thermal stuff, even if there's not much gas in solution. So 1.05 to 4. Okay? So it's a factor, it's not an order of magnitude anyway, even. It's about a half order of magnitude. And 3 is probably as big as you'll ever see, but you can get 4. Okay. So I'll write 3 and say that you can have 4. Okay. And then we've got RERW, but if you look at the rate equation, it's the ratio of log RERW, okay? So this also doesn't have units, but that number will typically be for, if RE is small, it means you have a lot of wells very close together. But even if it's like 100 meters apart, I said that was like Oklahoma City field in the 1920s and 30s. Even if you, so probably the very smallest this is going to get is 3 to 4. That's probably on the low side. And then it probably can reach close to 10. Now, I can try to calculate that just to double check, but so the largest RE that you're going to probably see in a field, realistic RE, is 5 kilometers, could be a little bit more. I mean, if you have a really high permeability gas field, you could have 5 kilometers between each well, but that's kind of at the limit. So let's put 5,000. That's really stretching it. 5,000 meters from the well to the boundary. And we said that the RW was about maybe 10 centimeters. So divided by 0.1. Shoot. 1,000. No, that was feet. No, meters. Yeah, meters. by 0.1. And then natural log, 10.8. Okay, so around 10. That's big as it's going to get. And then if we go down to 100 meters, let's see, make sure that 100 meters divided by 0.1 meter, and then log of that. So 10 meters, 100 meters. That's 7, so. This probably should be more like 5. At the very, if you go to 100 feet, that would be like 30 meters. That's 5.7. So it's probably, the lowest you're going to see is around 5 or 6. Okay, so just a factor of 2 in the extremes. Okay, those real extremes. Okay, so that's and of course you can put in these extremes and you can see what the range of JO will be. I'm not going to do that here for you, but a good productivity index, like in the North Sea, I think is like at least 1 stock tank barrel per day per 1,000 psi. That means, for example, like a Zecafisk, I don't know what it is, but let's say that you've got 7,000 pounds initial pressure, you draw it down to 2,000 pounds, that's 5,000 pounds of drawdown at a maximum. Okay, 5,000 times 1 with 5,000 barrels per day. I mean, that's good. I mean, it's not great because some of the wells in Zecafisk could have made 50,000 barrels per day with 5,000 pounds of drawdown. But so 1 is a good. So I don't know the complete range here. But 1 is good, and it probably can reach as much as 100 for really good stuff, really good oil wells. And probably you can still make money, I don't know, probably less than 0.01. I mean, just figure it out. I mean, you need to make, I mean, if a well costed a minimum probably $500,000, okay, and so you want to make $1 million to kind of make it worth your while over the life. So you want to make $1 million, and you want to make it over 20 years, okay? You got the patience. So $1 million divided by, what did I say, 20 years, divided by 365. That's $140 a day. So it doesn't take. So you want to make a couple of 3 barrels a day. I mean, that you can do in Oklahoma and still be kind of making money. But so with 0.01, if you have 1,000 pounds pressure drawdown, then you get 10 barrels a day. So it's probably a little bit less than that, but economic. But that's probably the range, 0.01 to 100. So maybe 10 to the 4th, or 4 orders of magnitude. Okay. Seems a bit much, but probably. Okay. So that was one of the things I wanted to go through, is kind of give you feel for this. We'll hold off on the gas to talk about what's the range of the PI. The J is not quite the same for gas. It's a little harder to deal with. Okay, because for reasons we'll talk about probably later today and Thursday for sure. Okay. Any questions? Okay. Okay, so that's the first thing. And then the next thing I wanted to mention is that PE is not usually available. It's probably not ever available, okay? Okay, so that's kind of one of the things. The second thing is that steady state is very seldom reality. But this guy Morris Muscat, who's kind of the father of reservoir production engineering, if you just start depleting a reservoir or the volume that the well is draining, and as you take stuff out, the average pressure drops because you're taking stuff out. What he says is that if you stop any time during the life of the well, at year 1 or year 6 or whatever, then if you take that as a snapshot in time, the well is behaving as if it was in a steady state condition, meaning that essentially you've got pretty much the same flux, mass flux everywhere. It's the same as what's coming out of the well. Okay? So, and that's called this pseudo-steady state, is basically a series of steady state conditions where, if you will, the average pressure at the outer boundary is changing as a function of time because you're taking stuff out. Okay? The well volume is depleting. Okay. What is available is what we call some average, and it's kind of a volumetric average pressure within the RW to RE for a radial cylindrical geometry within the drainage volume. Okay, it's just kind of a volumetric average. And there are methods, the pressure transient analysis, well testing people, Tom Yelmer here locally, they can tell you 16 different methods to come up with an average, volumetric average pressure from pressure transient analysis. Muscat was the first one to actually publish a method to do that. Okay, so even all the way back to the 30s and 40s, he shows how to come up with an estimate of that. So by measuring the pressure at the wellbore, when the well's shut in, you can extrapolate it to a volumetric average. Okay, so there's a lot of methods for coming up. So this we can actually, okay. Another thing that's not handled in this equation that we're gonna just introduce it here is that sometimes, because of the dam drillers, okay, which is the majority of you guys, okay, because of the dam drillers, we often damage, in other words, when you're drilling, you've got mud in the hole, right? And the mud is to prevent it from blowing out, the condo. So we don't want that. But that mud contains particles, okay? And what you want to happen is that you want, in a sense, the rock to be sealed off while you're drilling, in a sense. And so you get infiltration of some of the liquid in the mud and some of the particles in the mud, okay? So those particles move into the pores of the rock. So sometimes you get a low perm or a lower perm, which we refer to as damage, very near the wellbore. So from RW to RW plus might be 3 inches is all you need. Okay? But because it's kind of series flow, like electric flow in series and electrical stuff, you remember? Okay, if you have one little resistor, it can screw up everything, right? Okay, and so if you get just a small few inches of low permeability, it can really mess up the productivity of the well. Okay, so this is called damage, and it can be very localized. It can be just inches, or it could even be maybe several feet. The permeability being damaged. And we're going to call this skin. Okay, damaged skin. Okay. And it basically will add pressure drop. And we're going to say, basically, since it's so close to the well bore, we're going to say that we add this pressure drop at the well bore, at RW, basically.
But the skin doesn't have to be negative.
Yeah, the skin would typically, if it's damaged, this skin S, we use the term S, small s, will be greater than 0 for extra pressure drop. Meaning that the permeability in this damaged zone is less than the permeability in the rock. Okay? We've lowered the permeability. Now, the completion engineers, which is the production engineers, you guys are choosing, what you want to do. If you want to become a production engineer, you can be the glory guy or girl who goes in and cleans up the mess of the driller. So you add acid, you do something to remove that damage. And when you do that, you may even make things better. So you may make the permeability less pressure drop than you would have otherwise. So here we're not going to call it damage, we're just going to call it stimulated is greater than that permeability. Yeah. All right? That can happen. The Ecofisk is full of stimulated wells. It's made of chalk. The Ecofisk field, the chalk looks just like this. This is artificially manufactured, but it's about 40 to 50% porosity, believe it or not. It's white as white can be, except when it's full of oil, okay? And the Ecofisk formation is, at least the Ecofisk field, every well is stimulated with just a hydrochloric acid treatment, and it stimulates, 10, 100 feet around the wellbore. They don't generally create fractures, maybe not, but they stimulate and they get this enhanced permeability, because the permeability of this is around 1 to 5 millidarcies, and that's what it is in the Ecofisk field. In the worst case, 0.1 millidarcy, in the best case, 5 millidarcy. That's it. That's the range. Very narrow pore size distribution. But then they can stimulate it and they can get it to go a bit higher permeability. So you can get a negative skin by increasing its permeability. So this is not in the equation up here, but I'm going to add it. Okay? I'm going to add it. I'm preparing you for a new version, a more realistic version of this equation. Okay? So how are we going to handle this first? Okay, so we're going to use average volumetric pressure instead of PE in the equation. So this is our radius. This is at our wellbore radius. And for steady state flow, if we look at the pressure, where this is our bottom of flowing pressure, and I'm going to use a log scale here, if that's okay. When you derive this steady state equation, you could actually solve for the pressure as a function of radius. We didn't do that, but you could very easily. And what you would find is that the steady state assumption gives you a linear pressure gradient as a function of log of radius. Okay? Okay. If instead, let's use red. If instead we plotted radius with a linear scale, okay, then it would look like this. Okay? Probably even more extreme than that, than what I've drawn here. It's because as a rule of thumb, 90% of the pressure drop occurs in about the first 10 meters. Okay? So I've got to make this even a little bit more extreme to get that. Okay? So you're getting a lot of the pressure drop, the majority of the pressure drop in a very, quite near the well. Okay. So it ends up that this is the pressure profile for steady state. Now, if we use the log radius here, then this is about half RE if we're using a log scale. Okay, because this is 0.1 meter, this is 1 meter, 10, 100. Okay, it's kind of like that. So the half of the RE is way out here. Okay. This is meters. I apologize for mixing or maybe this is feet. So we're now out at 1,000 feet, something like that. Okay. So on the log scale, what you'll find is that it's probably even further out to the right than what I've shown. But it ends up that if you take this pressure here and you do all the integration, you'll find that the average reservoir pressure volumetrically is approximately equal to the pressure at a radius equal to 1/2 RE. That's what you'll find. Okay? No, I'm sorry. That's not right. 0.6. 0.6. About 0.6. Okay. Pretty sure. Yeah, I think that's right. 0.6. About 60% of the way out. If you could crawl out 60% of the way to the RE, measure the pressure, that would in fact be a good estimate of the average volumetric pressure. Okay. So what you can do then is you can rewrite that steady state equation as KH P average log 0.6 RE over RW. Okay? You're just picking that point in a different radius. But it's because I told you this. Now, you don't have to believe this. You can derive that yourself. I can't, but you can, probably, and prove it to yourself. But that's the way it is. And because Muscat and many, many other people have given us methods to estimate the average volumetric pressure, we have that, then we can use this equation instead. And if you take the log of 0.6, that's pretty close to minus a half, I think. I have to check this. Stuff that I don't do very often, so. Yeah, minus 0.51. So let's not get picky. So we could rewrite this equation, and this is often how you'll see it written. P average (141.2). I apologize for all this repeats. This is the same. Log RERW minus 1/2. This is the same thing. Okay, you can take the log of the 0.6 out, and that's minus a half. Okay. Now, if the outer boundary is not at a constant pressure, which it essentially will never be, okay? But if the outer boundary is kind of a no-flow boundary, if it's a no-flow boundary, in other words, you've got, I'm a well here, you're a well there, and if, you know, if we're sucking air, so to speak, okay, some of the air is going to move towards me, and some of the air is going to move towards my comrade here. I don't want to say he's sucking air, but somewhere in between, if he sucks harder than I do, he may suck air from here all the way to himself, okay? And I suck air from here to here. There's a no-flow boundary, and that's what the wells are creating, okay? And these no-flow boundaries, the pressure gradient is what? If there's no flow, if the velocity is 0, what's the pressure gradient? dP dr. Has to be 0. That means that this thing has to turn the corner something like that. Okay, that's what it's going to look like. So the profile is essentially identical except out at the very far end here. And this is for what we call pseudo-steady state, where we have a no-flow outer boundary. Okay? dP dr at RE of 0. Nothing changes much, okay? But the average pressure has to change because there's quite a bit of volume out here. So the average pressure has to be lower than in the case of steady state. So this is the condition for steady state, but the condition if you have a pseudo-steady state with a no-flow outer boundary, then the average volumetric pressure is very close to the pressure at 0.472. Why I remember that, I don't know. About 50% of the distance out, a little less than 50% of the distance out. That's for pseudo-steady state. Now, so that means that we can rewrite the pseudo-steady state equation as KH like that. But the log of minus 0.47 is minus 3/4. I can do that in my head, right? Okay. So that's just the same. I realize you guys can't do that. I apologize for that. But, the only consolation is that you're writing this equation once, and I've had to do it for like 40 years. So I mean, I don't know who's worse off. Okay? That's it. That's the equation you will most often see. Okay? That's the equation you will most often see. So it's good that you get used to it. This, if you see the 3/4, that means that this is our volumetric average pressure. It means that we're talking pseudo-steady state. And this is our main rate equation for oil. Okay? Okay, so we'll take a break and then